throw to somebody than they have to accept it. That's how things work.
What's that little type? Okay, I don't want it. Well, accept it. Here, socks. Here.
Oh, look how cute this dog is.
And we're live.
Oh, miss.
I wasn't trying to.
I was trying to get it in the recycling. That's what you put your water.
You might be getting a dog, and I'm really upset about it.
Yeah, that makes sense. All right, since everybody's here, I'm going to start. Oh, don't throw it away.
It doesn't fly well.
No, it doesn't. That's why when I threw it earlier, it didn't work.
I was trying to put it in the garbage.
All right, so.
I woke up at 5:45 and I got done.
Too late, don't care. All right, so yesterday we talked about these triangles, and I think you guys had trouble seeing what I was talking about, so I drew you some pictures. Check it out. Red triangle. This red. Don't worry about it. Just look up here. This is your problem. Okay. The number one problem with geometry is being able to see it, and you guys spend most of your time not even looking at it, which is a problem. All right, so red triangle right here. Everybody see it? Okay, cool. The red triangle has base A. And notice it shares the same height with the blue triangle, right? So red triangle, blue triangle have the same height, which means their areas are proportional to their bases. Are we cool with that? Right, that was one of our lemmas from the other day. Bailey, you with me? Okay. So red triangle, blue triangle have the same height, so their areas are proportional to their bases. Well, green triangle and pink triangle also have the same height. So that means their areas are proportional to their bases, also A and B, right? So I've got red triangle's area and blue triangle's area in proportion are equal to A over B. And I've got green over pink's areas equal A over B. So I've got something equals something and something equals something. I've got a statement like this. I've got red triangle's area over blue triangle's area. Let me get round out for the division bar. Should equal A over B. And that's true because the heights are the same. And then I also know that green and pink, their triangles are going to be, their area is going to be proportional to A over B. So green goes with A, right? So area of the green triangle, and then area of the pink triangle. They both go with their bases. And it's because their heights are the same. Is everybody cool with this statement? Yes.
If it's the red triangle is proportional to its base, then why wouldn't you write triangle ACD over A?
Good question, good question. So what I'm trying to say here, and I should speak more clearly, is that the areas are proportional, right, in the same way that their bases are proportional. Does that make sense? I should speak more clearly. Yep. So red triangle and blue triangle, their areas are proportional in the same way that their bases are proportional. Okay? And these two areas, for the green and the pink triangle, their areas are proportional the same way their bases are proportional. So this is a true statement. Does everybody dig this? Okay. So what I have here is proportion equals proportion equals proportion, right? Or ratio equals ratio equals ratio. Proportion is when you have two things. Ratio equals ratio equals ratio. And we know by our first lemma that if we have something like this, right? A over B equals C over D equals E over F, right? We can write it like this. So this implies area of this triangle minus area of this triangle over area of this triangle minus area of this triangle should equal A over B. Remember that was our first lemma, that we were able to take three congruent ratios, three equal ratios, and then write them like this. Is everybody cool with that? That's from the first page. So I got from here to here. Again, it looks weird that that's true, but it is. We proved it on the first page. Are we okay with that? Are we seeing what I'm talking about? Hello?
Yeah.
Yes? Awesome. Okay, I want to make sure, because seeing it's the battle. Now, you might notice, what is the area of the red triangle minus the area of the green triangle? Well, it's this orange triangle, right? You see the big red triangle? And if we subtract the bottom, the green, what we get left over is this. So the area of the orange triangle is what that stands for. So in other words, this means area of the orange triangle. And in the bottom, blue triangle minus pink triangle. Well, blue is this triangle. And we subtract the bottom pink. We're left with this, the yellow triangle. which I do not have a good pen for, so I'll use purple, I guess. This is purple. And that's going to equal A over B. Now that's really interesting because these triangles don't have base A and B, right? That's not part of their bases. Their base is this segment here and this segment here, or you could say this is their base, or maybe this, right? But this gets me these two triangles. And if you notice, there's a triangle here, and a triangle there, and a triangle here, right? And if I do this process for different sides of the triangle, I'll end up with different combinations. For this one, I ended up with these two, because I'm looking at A and B. But if I wanted C and D, I would do the process like this. I would say, look, big red triangle minus green triangle gets me this triangle, and that triangle should be proportional to its base, right? The base is the other two. Same thing here. So notice before I had these two triangles, right? Here and here, with this one left out. When I do it this way, I've got here and here with this one left out. And then if I go for E and F, same process, right? Red triangle minus green, blue triangle minus pink. I get these two, right? These two should go with those bases. Are you seeing that, or should I go over it a little bit slower and do it again? Okay. The key is to see it. It's hard to see it, but once you do, you're okay. So everybody get with my logic on the first page. Red triangle, blue triangle have these bases, so they should be proportional, right? And then green and pink also have the same height, so they should go with their bases, right? Green and pink go with this. Whenever I have something like this, I can take two of these and subtract them like that, and I'll get the other guy. That's our first lemma. We learned that on Monday. Well, what is red minus green? Red minus green is this triangle, the orange triangle. And then blue minus pink is this yellow triangle, which I did purple because I don't have a yellow pen, sorry. Cool? Same thing here. Area of the blue triangle, which is this, minus area of the pink triangle, right? Those should both be proportional to D over C, right? Let me say this again. Blue triangle and red triangle, they both have D and C, right? So they're going to go together. Pink triangle and green triangle also have D and C, so they're going to go together. When I subtract the blue from the pink, I get the yellow, so that should go with D. And the red minus the green gets me this, so the orange should go with C. It's the same thing I did before, it's just with C and D, right? Same thing here. I drew my red triangle and my blue triangle, so they have base E and F. If I subtract these two guys, I get this, so these should go with E and F. Are we seeing that? So, on page, I believe it's 5, I don't have page numbers in this one, I'm not sure why. What we're going to do is we're going to take those triangles, and we're going to set them up, and we're going to get this. So I'm going to zoom out. It's going to be hard to see my diagram, but you'll be able to see my writing because I'm going to write with the markers. Alright, so the first time I do this, I'm going to think of that triangle like this triangle, because they are the same triangle. This one's bigger. And what I'm going to say is that the red triangle and the blue triangle have the same height, so they should be proportional in the same way as their bases, okay? So I'm going to say that this triangle, and now I can't use colors, so I didn't color code my triangle. The area of this triangle, that's ACD, right? Am I out of black pens? Oh, no, they're all over here. Use Steelers. All right. So the area of this triangle, ACD, should be the same proportion as area BCD. Does everybody see what triangles I'm talking about? This triangle here and this triangle here. The left side and right side big triangles. Cool. And they should relate the same way as their bases do. Base A, base B. Other classes had a lot of success with not writing any of this down and just waiting till the end. It's up to you though, okay? Are we cool so far? Awesome. So, what other triangles have the same height and share base A and base B? What triangles?
ADG
Mm-hmm.
and BDG.
Yep, so these two triangles down here, right? So I'll write those like this. Let's use like light pink for this triangle. Area of triangle ADG. And let's use light blue. Are we good? Ladies, are we okay? Okay, I just want to make sure, because if not, I can stop. Right. Should also be proportional to those bases. Right. Now I could have written this where I just had equal sign and had this next to it, right? So all three are equal, so I'm allowed to do this. Therefore, I'm allowed to subtract these two and get A over B. Zed, you know okay?
Alright.
Are you confused about why this is true?
Yeah.
Okay, that's our first lemma. We proved that on the first page of the packet. When you have three ratios equaling each other, you can take the first two and subtract them in this weird way, right? Just literally throw them together over a division bar, right? And have it equal the third guy. This guy. Always true. Trust me on that. I know. I don't tend to do that on purpose. I really just did it to piss off 6 Hour because they weren't working very hard, and when they saw everybody that did really good big brain moves, it motivated them. So now, the key is that we know what this is, right? The area of this triangle minus the area of this triangle gets us this guy. Is everybody cool with that? That idea? Yep, area of this triangle minus the area of this triangle gets us this guy, right? Are we cool with that? And that is triangle ACG. Everybody see ACG on their paper? Right, that's what's left over. So I'm going to call that, let's use, I want a reddish color. Let's do this. And then this means that area of triangle ACG, that's what's left over after we subtract that, right? I'm just substituting this for this. Over, well, here's BCD. And if I subtract this triangle, this bottom part, what I'm left over with is this, right? BCG, very good. So I'll do another color blue for that. So that should equal A over B. And I'm going to show you why I decided to do all these steps. So I want to know what A over B equals, so when I put it into an equation, I can set the other side of the equation up, right? So if I know what A over B equals, and C over D equals, and E over F equal, when I multiply them all together, I know what that should equal on the other side, right? If I do A over B in this equation, I know I should have this on the other side, right? And then when I multiply those all together, things are going to go away. And here's how I know that. So right now I have these two triangles. That's what I just talked about. This guy here and this guy here are these two triangles, okay? So these two triangles are going to be my equation. Then I'm going to go after C and D. And when I do that, I'll end up with these two triangles equal C and D, right? Now notice, this triangle was already used here, right? So I've got some overlap. So things are going to cancel when I have that multiplication going on. And then when I go after E and F, I'll have these triangles equal E and F, E over F. And notice we've already used this one and this one, right? So those will end up canceling. And what will happen is everything will cancel by division. And when things divide out, what do they become? 1. And that's what we want, right? So I just proved that this triangle and this triangle here equal A over B. Are we cool with that? I'm going to do by the same dumb logic, instead of doing it for these two, and I'm going to do it for these two. Right? I'm going to say area of this triangle and area of this triangle are proportional to C over D, because they have the same height, right? Area of this triangle and this triangle are C over D. And when I subtract them, that means this and this are C over D. So this and this is going to be C over D. Okay? Then I'm going to do that for E and F the same way. This triangle and this triangle have the same height, so their areas should be proportional to E over F. And the areas of these triangles should relate to E over F, which means these should relate to E over F by that subtraction weird thing that I did, right? So I'm going to do same dumb logic for all of that. So I'm going to do this. Therefore, by same dumb logic. Oh my God, who cares?
60.
Does that matter when God has forsaken us? Yeah. The only thing that matters is if God has forsaken you or not. And if he hasn't, then yes, you can enjoy the weather. Otherwise, what's the point? I ask you. Alright. So, by same dumb logic, these triangles should go with C and D, right? So I'm going to write this triangle, ABG. Should go with C the same way that AGC or ACG, which if you notice, I already wrote ACG up here, right? Should go with D. I'll use a different color for D. How about orange? Okay. The reason I use the same color here because it's the same triangle. This triangle is the same triangle we used earlier for this, right? And then I also know, by the same dumb logic, these should go with E and F, right? And I've already used this one. That's triangle BCG, so it's this guy. To go with this guy, ABG, which I used here. That should go with E and F. Let's use pink and brown. So if you notice, I've got green on top and bottom. I've got blue on top and bottom. And I've got this maroon, chartreuse, burgundy on top and bottom. So when I multiply these, we have this triangle divided by this triangle. They're the same triangle, right? When you divide anything by itself, what happens? 1, right? This divided by this. 1. And this divided by this. 1. Okay, so I'm going to write that all out. So when I do A over B, and I multiply them all together, I get this. So A, B, what's up? It depends, actually. You can look it up. I know, it depends. Look it up. It depends. So, when I multiply A over B, C over D, and E over F, what is A over B? Well, it's this, right? So I know that it must be this on the other side. Also D, isn't it also that triangle? So I'm going to use the same color while I have it out. B, no yawning in math class, is this. Guys, we only have 3 months left.
Yes.
That's it. And then I'll never have you again, ever. Yep, it's happening.
I'll just cry. I'm kidding.
No crying.
Too late. Well, technically there's 4 more days, but I won't be that squares will be only 2 weeks.
All right, so check it out. When I multiply these all together, A over B is this, C over D is this, and E over F is this. And then the magic happens. Because we know what this means, right? Multiplication happens on the top, division happens on the bottom. That's all it means, right? So I'm doing this divided by this. 1. That becomes 1. And what's this divided by this? 1. And what is this divided by this?
That's what I wanted all along.
I know. You played me. You played me. I threw them all at once because I knew that would lower your chances of getting it. Therefore, it equals 1. That's it. Can you zoom out? Oh, I am zoomed out. Wow. I just had really big writing on the marker. So what does this mean? It means that if we have 3 Cevians that are concurrent, then it divides up the sides of the triangle into this relationship. And when you multiply those relationships together, you get 1.
I lost one of the pens.
Now the question is this only true when the Cevians are concurrent? Meaning, is the reverse of this true, right? If we know that this relationship is 1, does that only work when the Cevians all intersect at one point? And that's what we're going to project. That's the converse.
Schmidt, what is this thing?
Right.
Oh, does it work?
Mm-hmm. I picked up you at it.
I don't know. It's just here. It was like over here.
This one picks up you?
Mm-hmm. And the front of the class. But yeah.
You should do other videos besides that.
Okay.
I need a new pen because I want to
Take one of you, take other
It's
days.
my turn.
Yeah, I'm really studying letter.
Maybe. Over the summer, I'll get bored.
Or like one of you a letter.
Oh my god. Remember when I asked for your opinions?
You should have a letter.
Can you scroll down a sec? I need to see.
You know, look at Eagle again. You should have a
Got a new
letter.
one. No, I just got that one. Where is it? I
Guys,
don't
that's
know.
okay. I watched him through it.
You got it, Cody.
Yes, I'm a detective.
Or letters.
That's zero voiceovers. Or it's just
Wow.
ow!
Everybody's got dumb opinions. Okay, so,
Yeah.
are we seeing this now? It's a lot of writing, but it's a lot of same dumb logic. Also, did you notice I never had to write like by LPT or by vertical angles, right? It's all by algebra,
Yeah, like that.
right? So if you see the picture and you get the idea, you get it for one of those triangle sets, you get it for all of them, and then you plug it in and go, right? It's 3 things, and if you understand the concept, 3 things won't be hard because they kind of flow into each other, right? You know what your angle is? Got to get those weird triangles to go with the bases, right?
The last part number 3 is the part that I don't really get because I don't know like how from going to one to know which other ones to write.
If you turn your triangle, it might be easier. Big triangles go with C and D, right? Little triangles go with C and D. What's left over should go with C and D, right? You see what I'm saying? And that'll be the thing. And if you want multiple copies so you can color, I can give you that, okay? All right, so that's the idea. Now, this says that, again, if they're concurrent, then this should be true. Now, the question is the reverse true, the converse? If we know that this is true, if we get 1 when we multiply the sides all together, right, will that mean that it's concurrent? And the answer is yes, we're going to prove that. Now, before we can get into that, sit down.
What do you call that? Like one of our converse?
Well, like, we don't have to say the reason why.
Oh.
This is Ceva's theorem, right? That's what we just proved with Ceva's theorem. Okay, that says all the things in proportion multiplied together equals 1, right?
I like it when you say this might be this equals that triangle, but then when you start doing like ones that aren't even close to like, so like this one, this triangle right here isn't even close to D, but it was like somehow equal to C and D.
I'll show you. All right, so everybody that's talking, shut up, because you're going to have this question in a couple seconds. And I won't be upset, but it would be a waste of time. Or not a waste, it would just be less efficient, right? So, if I turn the triangle, you're fine, by the way. Big triangles, CD, right? Okay? These 2 triangles, C and D. So when I subtract them, I get what's left over, and that should be C and D. That's what I wrote. Return it, E and F. Big triangles, E and F. Little triangles, E and F. These triangles, E and F. Okay, that's what I wrote. I just cut to the chase using the same dumb logic. So I got these two to go with E and F. That's what I wrote, triangle BCG,
Oh, okay.
right? And triangle ABG go with E and F. Okay? That's the idea. Okay? So, the converse is actually much easier to prove, but it requires a technique that we haven't learned yet. So there's this thing called proof by contradiction. So instead of proving something true, you prove the opposite impossible. So here's the idea. We're on number, I think it's page 6, okay?
Yeah, mine either.
What do you mean it doesn't look like that?
It's different.
It's page 5.
Well, we already did page 5. We just don't have another page 5.
You guys don't have a page
That's the
6?
exact same thing we just did.
What?
Wait,
Guys,
you already did.
no, you've been writing on the wrong page. Go back at the top and look. That's not the same thing we just did. You've been writing on the wrong page.
Wait, did you go on the wrong page 5?
It might have been page 5. I don't have page numbers. Guys, I have this one. That's what we've been doing.
Yeah, that's what
Yeah,
we
that was
did.
page
That's
4.
definitely not what I was doing.
Okay, is that page 4?
Yeah.
Okay, and we did that yesterday. This is a review of that.
Wow.
My pages are almost up.
Oh my god. Big dummy juice. Big dummy juice.
Yeah, that was definitely, yeah.
So when I said don't write anything and you'll have better luck, right?
Listen, if you said,
Way to go. All right. So, and you guys already wrote it yesterday, right? So you had literally no reason to write it. Okay, so for this one, good news, bad news. It doesn't take much for him to prove this one, right? It's funny that you guys wrote the exact same thing as yesterday and realized that's what we did. That's a big yikes. So yes, but for this one, to prove the converse, it's actually much easier. So what we're going to do is we're going to prove by contradiction. So the idea of contradiction is we're going to say, look, I can't prove that true, but I can prove that it would be impossible if it weren't. So here's the idea. Like, for instance, how do I prove today is not Saturday? Well, I can't really prove that it isn't, but I could prove that, like, I could assume it is, and then prove that it's impossible for it to be true, right? So I can't prove that it's not Saturday, just like, here's the reason why, right? But I can do this. I can say, let's assume it is Saturday, right? Then why are we at school? Exactly. So it contradicts my assumption that it is Saturday, right? So my assumption must have been wrong, meaning that it must not be Saturday. So by contradiction, I prove that it isn't. Another example with math. Let me see if I can get you guys on board here. We're going to prove that when you add two even numbers, you get an even number. Right? 4 and 4 is 8, etc., etc. But we're going to prove that. So what we're going to do is we're going to say, look, here's an even number. How do I know that number's even? It's 2 times something. That'll always be even, right? Any number that's even is divisible by 2, can I divide that by 2? Yeah. What do I get? I get 8, right? Here's another even number. How do I know it's even? Because I can divide it by 2, right? And it comes out evenly. So, and then we're going to say, instead of that it equals an even number, we're going to assume that it equals an odd number, right? We're going to prove this by contradiction. Let's assume it's odd, right? So here's a number, and I'm saying C is odd. Okay? So I'm going to prove by contradiction that C can't be odd, which means it must be what? Even, right? Which proves what I want to prove, right? We're going to try and prove that C has to be even. I'm going to assume it's odd, show it's impossible for it to be odd, therefore it must be even, okay? So what I'm going to do is I'm going to pull out a 2 from both of these. Right? Cool. And I'm going to divide by 2. So I don't need parentheses anymore. So there's 2 possibilities. Case 1, C over 2 doesn't divide evenly. Okay? So it is not an integer. Right? Integers like -1, -2, -3, 0, 1, 2, 3, right? So C over 2 doesn't divide evenly. It's not an integer. It's like a fraction, right? Decimal, something like that. Now, if C over 2 is not an integer, this is a problem. Because A and B are, right? We said that they are both even, right? And A and B are whole numbers, right? Integers. So how do 2 whole numbers get you a fraction? You see what I'm saying here? If this was like, I don't know, 3 over 2, how do I take 2 whole numbers like 2 and 1 and get 3 over 2? It's impossible. Can you ever take 2 whole numbers and get a fraction when you add them together? No way. So this is a contradiction, right? Contradiction. That's what that symbol means. Not. Remember that from the beginning of the year? Go back and watch video 1. 2. C over 2 is an integer. But here's the problem. We said C over 2 C was odd. And if C over 2 comes out evenly, it comes out to an integer, like a whole number. Doesn't that mean C is even? Right? If I can divide that by 2 and get a nice number, right, an integer, this is what it says, right, then C should have been even. So that contradicts my original thought that C is odd. So is it possible for C to be odd? No, which means C must be even. If you didn't follow that 100%, all I want you to see is that I couldn't prove that this is always even. But I could prove it never can be odd, which means it must be even. I proved it by contradiction, right? I assume something to be true and prove that that's impossible for it to be, and so therefore it must be the other thing, right? That's the idea. So here's what we're going to do. We're going to assume that these aren't concurrent and show that it's impossible for this to be true if they're not concurrent. Does that make sense? Therefore, they must be concurrent, and this is true only if they're concurrent. So here's what I'm going to do. I'm going to draw a little line from here to here. I'm going to call that H for Hannah. So I'm going to say let.
Can you repeat it right?
Sure. This is not very long. I don't know. Ask somebody else. I don't have page numbers. Let CH and then let ADHB. So this tells you that I created a segment from C, right? Right? And then I made sure that it also created ADHB at the same time. Does that make sense? Nope. It just can't be D. And that's what this shows, right? D and H are separate points. Okay? Now here's the thing. Since this is true, we know that A over B should be the ratio of AD and BD, right? I'll pause for station identification. Right? So A and B, little b's, A and little b, are AD over BD. Cool. And I know A over B times C over D times E over F equals 1. What? No, that's given to us. We're proving that these are concurrent. And I'm saying, let's assume they're not concurrent, right? Let's assume that this is over here. So I know that AD over BD times BE is what C is, right? Over EC. We'll do CE, keep it alphabetical. Times CF over AF equals 1. Now we're assuming that this right here also gives us where all these equal 1, right? So that means that instead of writing AD for A, I should be able to write AH, right? Should be the same thing, if it works, right? I also know that AH over BD times BE, same dumb crap, I just switched out AH. But this is the problem. We said earlier that D and H are separate points, right? And if they're separate points, well, how can this both be true? Right, we'd have two different values here. What I'm trying to show you is that, look, when we cut this into A by A and B, there's only one way to cut it. If I've got a line segment, and I want to cut it right here to get a certain amount here and a certain amount there, is there another way I can cut it to get that same amount Right? I want to cut a board in half. Is there multiple places where you can cut it to get a half? No, there's one place where you can cut it to get half. If I want to cut it into A and B, there's one place I can cut it to get an A and B. I can't have this and this equal AB. That's a contradiction. It doesn't work, right? They're two separate points. So we say contradiction. Therefore, AD over BD equals AH over BD, which implies D and H are the same point. And if D and H are the same point, then there must be only one way this works, where the Cevian does go through G. So therefore, Cevians are concurrent Now, this is not saying all Cevians ever are concurrent, right? I can draw random Cevians all the time, right? What I'm saying is that if this is true, then the Cevians have to be concurrent. Because if they weren't, I'd have this going on. I'd be saying that, look, this length here is A, but so is this length here. And that's a contradiction, right? That can't be true. I can't have a length here and then a longer length be the same length. It doesn't work. If I've got an equation, let me do it from the board. If I've got an equation, 2x y equals 8. And I've got another equation. Let's do it like this. Let's even do this. Let's make it simpler. Let's make it simpler. Can x be something up here that's different than this x down here? No. They're both going to be 4, right? There's no other way to do it, right? Same thing here. If I divide it up into A and B, there's only one way to do it, at point D's. If H was a different point, then they wouldn't be equal to 1, right? They'd have a different representation here. Here I have an equation. The only thing I changed is this. If they still both equal 1, those have to be the same. Everything else is the same. Everything else in this equation is the same, right? Except for x. So even if I call that y, it's still going to be the same answer, right? X must equal y. Has to be. Everything in this equation is the same. So x and y have to be the same as well. Everything in this equation is the same, so AD and AH must be the same. Which means D and H are the same point. And if they're the same point, well then, yeah, it must have been concurrent. There's only one way to get it done. I know it's kind of weird, but that's the proof for it. It's proof by contradiction. We're showing that D and H have to be the same point. There's no other way. If H was a different point, this wouldn't be true, and we know that to be true, right? Today can't be Saturday, because we know that kids aren't at school on Saturday. So that would contradict our assumption that today is Saturday. So by contradiction, it can't be Saturday. I know this is true, so when I get something that says it's not, then I know that thing must be false. This can't be A, because that's A. So whatever this is would break this. Therefore, that's a contradiction. They must be the same point in order to make it work. Cevians are concurrent. I know this is a little weird, but the good news is that it's not a lot of writing. Create a contradiction, right? Create your other Cevian. You know, say, hey, if it doesn't matter where the Cevians are, I'll move it over here. Write stuff you know, and show your contradiction. I can't have two different things equal the same thing. So that must be the same, which means the points are the same, which means they're concurrent. I'll go over it one more time. Create a separate Cevian. Assume that they don't have to be concurrent, right? Write out the stuff that you're given. I wrote it out with big letters, right? We can't have the same thing, or two different things equaling the same thing, right? And those are two different things. Therefore, these must be the same. which means D and H are the same point. Therefore, Cevians are concurrent always when this is true. Otherwise, it would contradict what we have. Yes?
So how do you know that you have to do it this way?
So there are lots of techniques for doing proofs. This is the simplest way to prove it. It's just requiring a new technique that we haven't seen before.
It's like you can do either one.
So this one is giving you this and saying prove this. It's saying prove Ceva's converse, right? The other one is asking you to prove Ceva's theorem. Does that make sense? Okay. Yeah. So Ceva's theorem says if they're concurrent, then this happens. The converse says if this is true, then they must be concurrent. And we've proven that by contradiction. Because if they weren't concurrent, this wouldn't be true. And we know that to be true. That's given to us as true, right? So that's the idea there. So good news, bad news. Good news is not a lot. Bad news is kind of weird because it's different, right? But we're going to practice this some more. We're basically out of time for today. We've got a little bit of time left. What we're going to do tomorrow for Friday is talk about this angle bisector theorem, which is kind of bizarre. It's saying if these two angles are equal, then these sides relate the same way that their bases do. We will grade the quizzes tomorrow, and then we're going to jump into this. Fingers crossed. You've got one shot to finish your quiz before tomorrow in class. So you should see me after school today or during school.
But then retakes will still be allowed.
Yes, but we're running out of time in the quarter. There's only like 2 weeks left for retakes. Guys, if you want, if you've got a study hall or something or a free period for some reason, again, ask your teacher. I don't care when it is. Come on in. You can work on your quiz then. Like if you got free time next hour, awesome. Come on in. Sit in the back of the room.
I do, but I have nothing to do.
Wait, what is the
Oh, talk? Yeah, that's 7th hour. I believe it's the end of 7th hour-ish, homeroom, something around there.
What are we doing here?
It's the freshmen. If you were absent for Monday, or just need a refresher on these lemmas, please go back and watch the video. Shout out to Cheyenne, who yesterday taught my 3rd hour class for me, because I had to be gone for 3rd hour, so she taught what you guys learned yesterday that we went over today, and did a really good job. I gave her 5 maybe even 6 self-development points. I don't remember what. The reason I don't remember how many is because you almost had your full 20. I will give you guys how much you have after I grade all the self-development you guys did this weekend. I've got a super busy weekend up. I've got to work a spaghetti dinner and a bunch of stuff at one of my old schools. What? Yeah, whenever you come in for help, you get 2 points. Yes. I put points down for you.
I don't think I have
You probably don't. Awesome.
the paper one.
That's good. I will take a look at all those and I'll add them up. I've got a spreadsheet and I'll post them or talk about them Monday. 20 by the end of the semester.
20?
20.
Oh, I think I have like
Cheyenne, I think, has 17 already. I think a bunch of you already have in your teams. Not you necessarily, but like out of all my classes.
I think I have 4 from playing problems, and I did some worksheets back when you were on.
If you've come in at least, if you've come in twice a week, I can give you up to 4 points a week, right? If you come in a 3rd time a week, I can't give you points for that. But 2 times max. So if you've been in for help at all, you should have points for that. I will read off what I have right now before I add in the stuff you did this week. So Jerica, you have 2. Bo, you have 2. Bailey, you have 8. Cheyenne, 17. Guitar, 6. Nolan, 0. Autumn, 0. Zed, 4. Michaela, 10. Dylan, 0. Courtney, 4. Lindsay, 0. Keaton, 4. Taylor, 5. Calvin, 0. Shelby, 8. Hannah, 4. That's before I did the stuff you did on Wednesday.
Oh, okay. I was like, what did we do with that entry? You take them? Still have them. Okay.
Yes.
Come in.
Oh, you should. Why should you have 8?
What?
Okay, I haven't added those.
Okay, well, we don't talk
If
about
you're
it.
in School Bowl or something like that, we need to add those in. Okay? We'll do it right now. All right, so how many points? What does it say in the syllabus for School Bowl points?
I don't know. I just know that if I have to go through with that, then I'm going to get the points.
All right, I will add those in this weekend.
I never have to do it again.
That is the idea. Why are you never going to do it again?
I don't enjoy it.
I might join you next year and co-coach or something.
Great. I have not. I didn't want to do it.
Bartos.
I didn't want to do it this year either.
That's
Yikes.
the dream team right
What?
there. Brian Bartos.
You can show